For instance, you have the road noise, you have the wind going by, you have billboards or trees going by your window. None of that exists in space. The only way you get a visceral sense of how fast I was going is, you're going over the Pacific Ocean, and then 10 minutes later you fly over New York, and then 10 minutes after that you're flying over London.
If the ISS was orbiting closer to Earth, we'd all see how terrifying its speed is. It would cross the US from coast to coast in just 10 minutes, lapping the Earth more than 5,500 times a year.
But it's actually traveling at 26,000 kilometers per hour, or 17,500 miles per hour. So you'd definitely be breaking the speed limit, right?
Speed on Earth can be incredibly dangerous, but in space, at the velocity the ISS hurdles, the consequences of a collision can be off the scale catastrophic.
Space debris is going by you at about 5 miles a second, so if there's a big piece of debris that happens to have your number on it, it's moving so fast you'd never see it.
March 23, 2012, Mission Control radios the crew.
You'd never see it.
Any idea? Checking.
March 23rd, 2000 is heading straight for the space station.
The time of closest approach of this
2012,
fragment of space
Mission
debris
Control
is 11
radios the
minutes
crew.
from now.
No one knows how
You'd never see it.
Any idea? Checking.
March 23rd, 2000 heading straight for the space
You do what
station.
you're trained to do.
The time of closest approach of
and
this
even though you got
fragment of
woken up
space
in the wee
Mission
hours of the
Control
morning, you know what
radios
the
the crew
reason
now.
is.
No one knows how space station.
Checking.
March 23rd, 2000 heading straight for the space
Do what
station.
you're trained to do.
time of closest approach of this
Everything you have
fragment of
to
space
station,
Control
which takes about 45 minutes.
No one knows how space station. March 23rd, 2000 heading straight for the space station. Can withstand a sudden loss of pressure that would come from the hull being breached.
Coming up on the 6-minute mark.
If there is a puncture, any loss of air can lead to a serious emergency.
Coming up on the 3-minute mark until the time of farthest approach.
The crew takes no chances. They head for the escape vehicles.
We floated into our Soyuz spacecraft with initial preparations for undocking if space station were to be hit. And you just kind of hunker down and hope it doesn't hit you, and you just sit there and wait. Initial preparations for undocking if space station were to be hit. And you just kind of hunker down and hope it doesn't hit you.
Fortunately, this time it's a near miss. But the ISS cannot. Fortunately, this time it's a near miss. But the ISS cannot. Fortunately, this time it's a near miss. The
and those rockets are using propellant, and that propellant isn't infinite.
It all has to be sent up from Earth at a cost of $10,000 per pound of propellant.
And those rockets
This
are
brings
using
engineers
propellant,
face to
and that
face with the
propellant
greatest challenge of all.
isn't infinite.
How to reduce the station's
It all
reliance
has to be
on
sent up
Earth.
from Earth at a cost of
The
$10,000.
ISS can't be self-sufficient if it relies on thrusters to move. But a clever trick hidden at its is one option, but that uses up precious propellant.
With the space station, if here's the Earth, we want to keep the station usually, I mean, there are sometimes exceptions, but usually you want to keep the station in the
This is
same
one
relative
option,
orientation.
but that uses
towards-
up precious propellant.
With the space station, if here's the Earth, we want to keep the station usually, I mean, there are sometimes exceptions, but usually you want to keep the station in the
This is
same
one
relative
option,
orientation.
but that uses
towards-
up precious propellant.
With the space station, if here's the Earth, we want to keep the station usually, I mean, there are sometimes exceptions, but usually you want to keep the station in the
This is
same
one
relative
option,
orientation.
but that uses
towards-
up precious propellant.
With the space station, if here's the Earth, we want to keep the station usually, I mean, there are sometimes exceptions, but usually you want to keep the station in the
This is
same
one
relative
option, but
orientation.
that uses up precious propellant.
With the space station, if here's the Earth, we want to keep the station usually, I mean, there are sometimes exceptions, but usually you want to keep the station in the
This is
same
one
relative
option, but
orientation.
that uses up precious propellant.
With the space station, if here's the Earth, we want to keep the station usually, I mean, there are sometimes exceptions, but usually you want to keep the station in the
This is
same
one
relative
option, but
orientation.
that uses up precious propellant.
With the space station, if here's the Earth, we want to keep the station
600 RPM.
usually, I mean, there are sometimes exceptions, but usually you
The
want to keep the
flywheels
station
create a lot of
in the
angular
same
momentum
relative
simply by
orientation.
changing the RPM or tilting the plane they spin in.
They
They transfer that momentum to the ISS, and the whole thing moves.
If I were sitting here in a chair and I had a gyroscope spinning around in this direction, and all of a sudden I put a brake on and slowed down the gyroscope, the chair would start to spin around. No, I would slow the gyroscope around, and then if I were sitting here, I would do a big spin because that angular momentum has to be conserved. The brake on and slow down the gyroscope, the chair would start to spin around. No, I would slow the
The International Space Station is the ultimate extreme home.
Space is an environment where human beings were not meant to live.
The most expensive structure humans have ever built. Here, in the most inhospitable environment known to man.
The only reason we can go there is by taking technology to provide us with everything that we need in order to stay alive.
With no air, food, or water, 250 miles above the Earth, it's an epic engineering challenge.
We as engineers are having to figure out how to make systems that provide all those functions that Earth provides in a tiny little can.
To reveal how the engineers pulled it off, we're going to take it apart and uncover what's going on inside. How the International Space Station and its superstructure secrets will help our species reach other planets and beyond. Costing up to an astonishing $150 billion. This is an unprecedented home.
The ISS is an extraordinary feat of engineering because not only do you have to make this big environment that people can live in, which, you know, is non-trivial to do on Earth, you have to do it in space.
It comprises millions of high-tech components. There are 16 pressurized modules with living quarters, sleeping bays, an observation deck, and 6 science labs, all connected via airtight tunnels. There's plenty of parking for visitors, including spots reserved for Russian Soyuz capsules, and the ISS's lifeboats, which are on permanent standby in case of emergency. Unlike any other structure, the ISS has to provide everything its astronauts need. If it fails, they die.
A human being can only survive for 3 weeks without food, 3 days without water, and 3 minutes without air.
For humanity to successfully venture well away from Earth, astronauts will need to be self-sufficient. If the ISS can solve the challenges, it will prove humans can truly live in space. But before anyone can take up residence, the engineers behind the ISS had to get it into space. And it weighs a colossal 460 tons. The same as about 300 cars.
It would be great if we could just build the International Space Station on the Earth and then just blast it into space.
You couldn't just fly the whole thing up there in one shot. You had to take a piece at a time and assemble it together like Lego.
The ISS began life as just 2 modules that had to be connected in space. One built by America and the other by Russia.
The first flight actually launched in November of 1998. Hadn't been that long since the end of communism in Russia, and here we were building a joint Russian-US space station. So just the political milestone that represented was pretty significant.
After the intense competition of the space race, it's suddenly all about collaboration. The orbiting Russian module is known as Zarya, which means sunrise. Next, the first American module, known as Unity, sets off inside the cargo bay of Space Shuttle Endeavour.
Liftoff of the Space Shuttle Endeavour.
Unity is now chasing Zarya through space at more than 17,000 miles per hour. 2 modules from 2 superpowers are about to dock.
First thing we have to do is to open up the payload bay doors.
Can you imagine how important it is for these 2 modules to mate?
Unfortunately, before both modules were launched, engineers spotted a problem.
Not all the pieces got to be integrated on the ground before they were launched.
Neither Zarya nor Unity were originally designed for the ISS. Their docking systems wouldn't fit together.
The Russian hatches are all round, and our hatches are all square.
I mean, this is fundamental to the International Space Station, and what you have are 2 things that don't mate.
And so, what do? Well, you make an Adapto-Lego block connector thing.
The L-shaped Lego thing they came up with is called the Pressurized Mating Adapter, or PMA. Not only does this accommodate the different shaped hatches, it also has a precision-engineered docking ring for grabbing hold of another module and perfectly aligning it. Vital if a reliable airlock is to be made. This is the moment of truth. Latches on the inside of the docking ring finally make the connection and pull the modules together.
Houston Endeavour, we have capture of Zarya.
The International Space Station is born.
It was amazing. I mean, here we are. We got airborne. We had Unity in the bay. And when we left a functioning space station ready for the next module to come up.
In the 20 years that follow, engineers from all around the world join the project, building their own space laboratories and bigger living quarters. But every one of the modules was constructed on Earth, and it takes a supreme international effort to launch them all successfully into space.
It took a long time to build Space Station. We have to fly everything up, we have to connect all the modules, put them together. So that took over 40 missions. Modules came from all over the world. We have the US modules from NASA, we have the Russian modules, we have the Japanese modules and the European module, you name it.
And it costs around $10,000 to send every pound of weight up here from Earth.
So right now, we're in the Japanese laboratory. It's one laboratory out of many here on the International Space Station. This is Columbus, the European module. It has science experiments all over. You could see it looks a little bit crowded. Here we are in the US laboratory. Again, this is a laboratory with science experiments on all of the walls here. So we're going into the Russian segment. Be ready. You don't need a passport either. And what's cool about this module, it is actually the very first piece of the space station that came up in 1998.
It's been occupied continuously ever since then. So if you think for 18 years, there has always been a human presence in space.
Today, the ISS is enormous. By far the largest space station ever created.
It's actually big enough if you have a good pair of binoculars, and when it's flying over, right overhead, you can actually see it. Normally you look at a satellite and it's just a little dot, but the ISS is big enough that you can actually see it as an extended object.
It's so vast, in fact, that it would dwarf Times Square. At an astonishing 357 by 240 feet, it has more living space than a 5-bedroom home. But the larger the International Space Station becomes, the larger a very obvious issue becomes too. Air. In space, there is none.
It doesn't provide a life support system for us, air, oxygen. And so if we have a home in space, we need to provide all of that.
The average adult breathes close to 4,000 gallons of air per day. With a crew that can be up to 9, the ISS must supply a huge amount of it. And it's not coming from outside those windows. Cruising outside the Earth's atmosphere, the International Space Station has to provide everything the astronauts need to live. And breathable air is first on the list.
Their very survival really depends on the things that we provide them. And you're also having to deal with the fact that at any point in time, if one of your system fails, you have a very limited amount of time to either get something from Earth or to get back to Earth as quickly as you can.
In a crisis, an emergency supply of oxygen can be sent up by rocket.
3, 2, 1.
With technological advances, spacecraft can now rendezvous with the ISS in 6 hours, if everything goes as planned. But even when a cargo delivery is successful, there's a price to pay. The cost of each mission is colossal, almost $200 million.
It's expensive to bring a kilogram of anything up to the space station. And to spend all that money just to bring up water and oxygen would be an incredible waste.
The ISS needs to make its own air.
The oxygen on the ISS can come from a delivery from Earth, and then they're stored in tanks. But the ISS is also capable of generating oxygen on board.
On Earth, we take air for granted. In space, each astronaut must be supplied with 1.85 pounds of oxygen per day, 365 days a year, to avoid suffocating. In the very heart of the ISS is an unassuming machine about the size of a trash can. It's this that holds the secret to keeping astronauts alive. Incredibly, it generates oxygen from nothing more than water.
So what happens is you have some water, you feed some electricity through that water, and the electricity will split that water into hydrogen and oxygen.
The oxygen comes off as bubbles at the positive electrode, the hydrogen at the negative. But again, being in space turns something that's straightforward on Earth into a major engineering challenge. The bubbles of gas won't come out of the water.
In your high school chemistry lab, the gas just bubbles up to the surface because the gas is lighter than the water, and therefore it goes up. Gas is not lighter than liquid in space because gas doesn't have any weight and liquid doesn't have any weight. So you produce gas bubbles and they just sit there. And what we generally do is we centrifuge it. So you spin it all around, and the liquid, being denser, it doesn't weigh anymore, but it still has mass. So it's denser and it goes to the outside, and you can then separate the liquid from the gas.
The hydrogen gets thrown away, gets pumped into space, and the oxygen is used for the ISS air supply.
There's enough capacity on board to generate 5 to 20 pounds of oxygen a day. More than enough for the crew. In the extreme environment of space, making air is just the first challenge. The ISS has to keep it, but it's under constant threat of a breach in its hull.
There is so much space junk up there now.
There's the potential for it to